Okay, so we're going to look at some just kind of slightly different stuff today, some properties of polynomials as they relate to, kind of what the graph would look like. I'm never sure where to fit this into this unit. I think it just makes sense to take a little break and look at this stuff now. We'll come back at the end and we'll do some more in-depth graphing of polynomials. Once we have a bunch of we have to learn how to factor polynomials and find the zeros of polynomials. And then once we know how to do all that fancy stuff, we can come back and we can take this idea of what the graphs look like and we can go much further with it. But for now, just introducing some ideas about polynomials. So this is more sort of theoretical stuff. What is a polynomial? Well, this is our general form of a polynomial, and I want you to get used to seeing stuff like this. This is a mathematical statement, and it probably looks troubling when you're first in algebra. You see all those symbols up there. When you see lots of dense symbols, it just tends to just cause you to panic a little bit. But I want to get you past that. I want to get you to a point where you just kind of can relax and settle into this and just look at what this means. It shouldn't be that intimidating. I know it is at first, but I don't want it to be. So what is this saying here? First of all, what's that ... mean? When you see an ellipsis in math like that, yeah, just and so on and so forth, right? It's just going to continue that pattern, in other words. So we said a polynomial is a sum of terms. Well, this is just our way of saying it's a sum of terms. F of x is a polynomial if it looks like, and look, I've got these subscripts here too. Okay, I want to talk just very briefly about what a subscript is. So a superscript is, you guys know about this, right? I mean, like just from using technology, right? A superscript is something that's raised above the level of the regular row of text. Subscript is something that's kind of pulled down a little bit instead. They have specific uses in math. Superscripts are exponents. We know that. We've had lots of practice with that, right? Subscripts are used to keep track of things. They're an index. So when we say something like a sub n, that's saying, okay, this is a specific value of a is standing for, the letter A means it's going to be a coefficient. And the subscript is telling you, okay, which coefficient is it? We're going to keep track here. A sub n is the coefficient of x to the n. So whatever x to the power of n, whatever n is, and n couldn't be anything. If it's a polynomial, do you remember what has to be true about the exponents? What kind of number set do they have to be included in? Whole numbers, right? So n has to be a whole number. If we write this in standard form, what does that mean again for a polynomial if I've got a bunch of terms with different exponents? What does standard form mean if I write the polynomial in its standard organized form? How would I write down the various terms? Alphabetical. Okay, assuming we have only a single variable, which we mostly will, like only x's. How do I know which term goes first? Highest power. Okay, good. So the highest power of x, and then we're just going to step down through the powers until we get to the weakest, right? Okay, so then we know that this is going to be, n is going to be our biggest whole number exponent, right? Whatever that is, it might be 10, it might be 111, who knows, right? But whatever that power is, a sub n just represents whatever number is being multiplied by x to that power. Notice that the n's go together here, right? Okay. So a sub n just is a number. It just stands for a number, okay? So there's our first term. Okay, there's our first term in our polynomial. What's the next term going to be? Well, the next term is going to be the next power of x, the next power that it could be, would be x to the n minus 1, right? Because if n is the biggest whole number power of x, then the next biggest would be 1 less than that, right? Because whole numbers, they advance in increments of 1, right? And then a sub n minus 1 is just going to be whatever coefficient goes with that power of x. So once again, this is just a number, right? It could be 0. If that term isn't there, right? If there is no x to the n minus 1 power, let's say n is 10, then this would be 9, wouldn't it? Maybe there is no x to the 9th power, in which case that coefficient would have a value of 0. Okay, we just wouldn't write it. Does that make sense? And we just work our way down. Then the next term would be x to the 1 less than n minus 1 would be n minus 2, right? And so whatever that coefficient is, we're going to call it a sub n minus 2, just to keep track. And I don't want to write out the whole list because we don't know how long it is, right? We don't know the value of n. It could be a million. So I'm just going to put this ellipsis, this plus dot, 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 plus, which means, and so on and so forth until we get to the end, right? We're going to step all the way down. Our very last three terms would be x squared times a sub 2 plus x to the 1 times a sub 1, right? Plus, there is an invisible x to the 0 there, but I wouldn't write x to the 0 because it equals 1, right? So x to the 0 times a sub 0 just is the same thing as a sub 0. I wouldn't even write it. That's what we call our constant. Okay, makes sense? And I'm not sure, okay, this is kind of dumb. I don't know why they have the dot, dot, dot there. I'm going to get rid of that because that's kind of confusing and dumb. We're done at this point. There, that's it. So you might scratch that off of your notes. Okay, questions on that? Does everybody see what that all means now? Okay, so next time you see stuff like that, don't panic. Just kind of think in terms of, okay, what's the structure here, right? Now you've seen a structure like this. You'll see this stuff again, okay? So just quick reminder that the coefficients have to all be real numbers. They can't be imaginary. And the exponents have to be, they have to be whole numbers, don't they? Here it says positive integers because they didn't put the 0 up there. But just think of them as being whole numbers, right? Okay. So what is then that a sub n is kind of special because it is the coefficient that goes with the biggest power of x, okay? If we write this in standard form, we call this biggest power of x, ooh, yikes. We call this first term, the one that has the biggest power of x, we call that the leading term. Leading just means it's first. It's out in front of the pack. Okay? So then what do you suppose that coefficient in that leading term is called? Any suggestions? Any guesses? Say it again. It is. It's the leading coefficient, exactly. There it is. Okay, so let's just look at some examples then. So from this list, I'm going to give you a bunch of polynomials. Right? Top one's a monomial, but monomial is just a subcategory of polynomials. So what's the degree of this polynomial here? 0. It's 0, isn't it? Because the biggest power of x is x to the 0. What's the leading coefficient? 4. That's kind of a dumb example. We would rarely ever think of that as being a polynomial. We just always think of that as a constant, right? I mean, we don't. That's a little overkill. Okay, what about this guy here? What's the degree of this polynomial? And the leading coefficient? Okay, degree? Leading coefficient? I mean, you got this, right? Let's do one more. How about this one? Degree? Leading coefficient? Boom, you got this. We don't need to do any more of that. You got it. Okay, so what about this one then? What's the leading term? What's the leading term? Negative 1/2 x cubed. Bingo. Okay. First term when it's written in standard form. Okay. Leading coefficient, negative 1/2, the degree, 3. And quick reminder, what do we call, if it's degree 3, what do we call that? Cubic. There you go. Good. If we want to be fancy. Is that a big deal? No, not really. Okay. Andrew and Abby, you guys can hear me okay, right?
Yep.
Okay.
We can't see the screen, though.
Oh, you can't see the screen?
No.
Oh, man, I thought I did that. That's crazy. Can you see it now?
Yeah.
Okay, there you go. Oh, so in the future, just yell at me when that happens, so I know right away. Okay. So let's take a quick look at what our polynomial parent functions look like, and we know some of these. A constant function. You take a second and think about what these would be, how you'd write these things. Okay, how would you write down the most basic form of these four functions? And let's go ahead and use like function notation. So f of x. The most basic form. Okay, how about this one? What's the most basic form of a constant function? F of x equals, could be 0, could be 0, could be 1. We're just going to call it any constant. We'll just call it c, how about? And that just looks like a horizontal line that's at y equals c. Okay. All right, what about linear? The most basic linear function would be what? F of x equals, think back, I think we did this one a long time ago. Just x would be the most, and mx plus b would be our kind of our basic all-encompassing, that's like standard form kind of, right? We call it slope intercept. But the most basic would just be f of x equals x. Okay, and remember that's just going to be, oops, can't do that. That's just going to be a line through the origin, right? Oh, come on, don't quit on me here. There we go. Okay. With a slope of 1, so that's probably close enough, right? Okay. Our most basic quadratic. Okay, remember what's the graph of that going to look like? Parabola, okay. Something like that. Most basic cubic. X cubed, okay. And remember what that one looked like. It looked like kind of like that. Okay, what about quartic and quintic? What's quartic going to be? X to the 4th. And quintic would be x to the 5th. Okay, I want you to notice what their graphs look like. If I graph a quartic function, now this is, I'm limited by my algebraic, or by my artistic ability here. But that's kind of what a quartic function looks like. It looks a lot like a parabola. What's the difference? It's a little more squared off. Okay, and I'll pull up Desmos in a second. We can look at some examples of that are graphed a little better. What do you suppose a quintic function is going to look like then? Yeah, it's going to be a more squared off cubic function essentially. Okay, so it's going to look kind of like that. Okay. Let's look at these on Desmos where we can get a more, just better representation. But I want you to see, how are they related? So I'm going to do f of x. I'll show you. You guys got messing with Desmos is kind of fun. I'm going to do x to the n. Oops. And notice it asked me if I want to add a slider for n. Yeah, I'm going to. Okay, and I'm going to let n go from. I'm going to let n go from 2 up to 10 in steps of 2. Okay. All right. So now watch what I can even hit animate on this. And if I go, let's make the properties, make the speed kind of slow. Now watch this. Oh, that's going pretty slow. That's going too slow. Oops, there we go. We'll do that. Watch what happens to this as we step up the, go up by 2s. Oops. Look what it does. It just flattens out more, doesn't it? The sides get steeper, the walls get steeper, and it gets more squared off. If I zoom out a little bit, let me do something like this, and I'm going to set up this window just a little bit better. So we'll go from x-axis, goes from something like -4 to +4. Let's try that. Okay, you get the idea, right? Okay. All right, now let's take another function up here. So those are what we might call our even power functions. When you have a monomial like this, when you have a monomial function that has a power of x, a whole number power of x, we call that a power function. Okay, you could think of a polynomial as just being a sum of power functions, different powers of x. Okay, the even power functions all have the same look, don't they? Even power functions are just power functions with even exponents, even powers. They all have kind of that basic parabolic look. They just get more squared off as the even power gets higher, right? Okay. And if we pick something, what if I pick, I'm just going to set n to be real quick. I'm going to set n to be like 100. I mean, look at that. It almost looks like a rectangle, right? If I set n to be 1,000, I mean, it really looks rectangular, doesn't it? Okay. Okay. Let's look at, but we'll leave it at 2. Okay, let's look at the odd power functions. I'll call this g of x. M. Okay, we'll add a slider for m, and m's going to go from 1 to, how about 11 by 2s. Look what it does. It's just what we said. The walls get steeper, right? And it gets more flattened out. Okay? But those are just, many representations of the stuff on the right edge of this. Where's my cursor? Stuff on the right edge of this chart that we just created, right? Those are the odd power functions. Okay? What do you notice about the end behavior of the even versus the odd power functions? So what do we mean by end behavior? We talk about that a lot in calculus, right? We've done a little bit of this before. Remember when we did our parent graphs and we made those tables? End behavior is what's happening way out to the right and the left as x approaches positive infinity or negative infinity. What's happening to the left and the right on all of these even functions? As I go far to the right, as x approaches infinity, what does f of x or y always approach? If I go far to the right, I'm going far up or down? Up, right? So as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x also approaches infinity, right? So we'd say that the end behavior, it rises to the left and it rises to the right, okay? Odd doesn't do that, right? Odd, it's doing opposite things. It's falling to the left and it's rising to the right. Okay, so let's see if we can. Seems like I forgot a slide here, but I don't think it's a big deal for you guys. I think I can skip this. No, I guess that's it. Oh, well. Oh, there we go. Okay. So then if we have an even degree polynomial, right, or the leading term, right, the leading term is even, what do you suppose is going to happen? I got another really cool thing I want to show you. This is, I don't have this queued up, but you show this to my calculus classes. I want to show you guys this too. You'll like this. Give me just a second here. I got to go down to... There we go. Okay, so I've got this polynomial up here. There's my polynomial. Look, I've got this really tiny coefficient of x to the fourth, plus a fairly tiny coefficient of x cubed, plus a tiny coefficient of x squared, plus x. Okay? I want you to tell me here, what is this thing? Which of these really seems to dominate? So on this scale, if I'm zoomed in pretty far, which term of my polynomial, here are the four terms, right? Which term seems to dominate? X does, right? They look identical, don't they? So do you suppose that's going to be the dominant player when I graph this polynomial? You'll think it's going to be X when I zoom out? Let's find out. If I zoom out a little bit, yeah, it sure looks like it. Sure looks like X is, man, that fits it pretty well, doesn't it? Seems to win. Uh-oh, things are changing. Things are changing, aren't they? Okay. So now at this point, X doesn't match it very well. I've zoomed out a little bit and X doesn't match it very well. Now that polynomial seems to match it better, doesn't it, as I zoom out? The green one. Everybody agree? Okay, but if I keep going, if I keep zooming out, the green one all of a sudden doesn't start to match it very well because it deviates away again, right? Let me change the x-axis. I'm gonna have to do this a few times. Because these functions, because they're power functions, they grow vertically a lot faster than they grow horizontally, right? So I got to keep kind of squeezing this thing in. So let's go. Like that, maybe. We'll start there. Okay, at some point, this thing starts to deviate. Remember, our original function is blue. It starts to deviate away from that green function. Well, let's see. Now it's starting to look more like the x cubed function, isn't it? As I zoom out. They look pretty similar, right? It's definitely the orange is the best representation of the blue function now, isn't it? These other ones, we can pretty much just get rid of those. They don't fit anymore, right? If I keep going out indefinitely, though, what's definitely going to happen? What do you suppose is going to happen if I keep zooming out on this thing? It definitely is going to turn again. And how do we know that? Okay, because the leading term has a degree of 4, right? So if I keep going out, I should see this thing start to turn again and start to match that quartic function. Well, there it goes, right? Everybody see that? It's going to turn up again, okay? Right, look at that. So it's starting to match, and I can just get rid of that orange one now. And now we can see that the blue and the purple, they start to match more and more closely, don't they? And if I go out far enough, I want you to see something. This is pretty impressive. If I zoom out far enough, boy, they're looking pretty similar, aren't they? Right? Getting pretty big numbers there, and now they're essentially indistinguishable, right? Okay, that's a pretty cool story. Pretty cool story. So what's that telling us here? That's telling us that even though the coefficient of that x to the 4th of that leading term, the leading coefficient was really tiny, right? Eventually, if I let x get big enough, and there's no limit on how big x can get, as x approaches infinity, what's going to happen? Well, look at the behavior of these terms. As x approaches infinity, the linear term approaches infinity, the quadratic term approaches infinity, the cubic term approaches infinity, and the quartic term approaches infinity, right? So they all seem to, but which one approaches infinity the fastest? The quartic term. In fact, how much faster does the quartic term approach infinity than the cubic term? Infinitely. So the moral of the story is the leading term dominates the polynomial, the end behavior of the polynomial. If I go out far enough, all this other stuff just becomes background noise, and only the leading term is really important when you get out far enough. The rest of it is just tiny. You can't even see a difference, can you? You can't even see that there's this other cubic and quadratic and linear terms are even there. If I go out far enough, they just disappear in the background noise. And the behavior of the function becomes dominated by its leading term. So that makes it easy for us to analyze the end behavior of a polynomial. All we have to do when we want to analyze the end behavior of some big fancy polynomial is look at which term? Leading term, right? Whatever the parent function of that leading term is, that's going to be the end behavior of the polynomial. Okay, make sense? Okay, so let's look at a couple quick examples then. Okay, so what's going to happen if I have, got to do one more experiment. Boy, Desmos has helped so much. You get to see these things in just in a realistic way. Okay, so I'm going to put up, how can I do this? Don't look at I'm going to try to make this graph like way over there, and let's just kind of scoot it over so you can't see it right now. If I do f of x equals negative 2.31 x to the 4th, what's that going to look like? What's the end behavior going to be? Oh, okay, how come? The x to the 4th, it's an even function, so it's going to have positive end behavior, right? But what happens when I multiply that function by a negative? It flips it, doesn't it, right? Because the negative 2.31 just acts like a vertical dilation factor for that quartic function, doesn't it? So it's going to stretch it by a factor of negative 2.31. So it's multiplying the y values by negative 2.31, so they get bigger and flip, don't they? And so if we look at this thing then, there it is, right? Okay, what if we do something like, I'm going to do negative pi x to the 41. What's the end behavior going to be? What's the left end behavior going to be? Okay, it's going to, the left end behavior is going to be up, right? How come? Okay, yeah, because it's going to be the flipped version, because I multiplied by a negative, right? And so it's going to be the flipped version of these odd power functions, right? Normally an odd power function is going to descend to the left and rise to the right. But if I multiply by a negative coefficient, it's going to flip that whole thing and potentially stretch it, isn't it? Right? Does that make sense? Okay. And let's look at this one. Sure enough, there it is, right? Rises to the left and falls to the right. Okay. So we could make some representative sketches then. What's this going to look like? If I had, are they going to be exact? No, because it's going to vary. The exact shape is going to depend on how big the exponent is, how squared off it is. But we don't care so much about that. We just want to know the end behavior. So if I have a positive leading coefficient and an even degree, what's the shape of my curve going to be? It's going to be up on both ends, isn't it? It's going to look something like that, isn't it? My end behavior, okay? What about in the middle? In the middle, it could be doing all kinds of crazy stuff. We don't know, right? But if I zoom out far enough, it's going to look like that, okay? What if I have positive leading coefficient and odd degree? So it's going to go down on the left, up on the right. Good. So we know it's going to look something like that, isn't it? Okay. If I have a negative leading coefficient, what's it doing to both of those? Just flipping them. Yeah. So it's just doing that. Right? Okay. So you tell me here, for 7 and 8, I just want to know, and everybody think about this on their own for a second before we say anything. I want to know the sign of the leading coefficient and whether the function has an even or an odd degree. So 2 parts. Sign of the leading coefficient and even or odd degree. How about 7? Negative, even. There you go. Good. How about 8? Positive, odd. You got it. Okay, good. All right. We don't have to do all these. Let's just do, how about if we do number 2? As x approaches infinity, f of x approaches what? Negative infinity. Okay, good. As x approaches negative infinity, f of x approaches negative infinity. And the reason being, if I look at the behavior of that leading term, that's the behavior of the leading term, isn't it? Okay. How about 4? As x approaches infinity, f of x approaches negative infinity, right? As x approaches negative infinity, f of x approaches positive infinity. And the reason being because there is only one term in this case. That's the leading term. We know that if it's a negative odd, it's got that shape, doesn't it? Okay. Okay. We've probably done this enough. Let me scoot up. We can. These are just various different types of questions from the homework. Real quick, which one's that? A, B, C, D, or E? It's A. Everybody agree? Rises left and falls right. There you go. Whoops. Okay, how about that one? That's a little tricky, right? A little bit tricky. But if I were, we didn't see anything like that, right? This is kind of that's a transformation of an x to the fourth. That's one way to think about it, isn't it? It's an x to the fourth shifted where? Shifted to the right by 4. Everybody agree? Okay. Shifted right by 4. Okay. That's one way to think about it. Another way to think about it, though, would be like this. I could just say, if I were to expand that whole thing out, I'm going to get x to the fourth plus other stuff, right? My leading term is just going to be an x to the fourth. If I were to multiply that out, that whole thing out, everybody agree? Okay. So that's all I care about is the leading term. So it's going to act like an x to the fourth. So it's got to be this guy, doesn't it? Okay. How about something like that? If I were to multiply that whole thing out, what would the leading term be? It's going to be x to the fourth plus a bunch of other junk, right? Okay. I think we've done enough of this. Probably done enough of that. What I want to get to, and I didn't quite get as far as I wanted to. It's all right. What about that one? What's the leading term of that polynomial? So from this part over here, I'm going to get an x to the 14, aren't I? From this part over here, I'm going to get an x to the 9th is my leading term. And if I were to expand the whole thing out, then what would I get? Yeah, x to the 23rd. Okay, so the degree would just be 23 of that one. Okay, that's good. Good place to stop. I'll put the assignment up. You can get started on it. There's a few other little wrinkles I'll add next time, but that'll get you going. All right, have a great day. Oh, yeah, clean the desks. Whoops, for sure. Thank you for reminding me.